All right, are we ready to rock here?
Yes, so.
We're recording. We got a sound check. Everything looks good. This is a good volume. I can.
This is a very good volume.
Yeah, we've been kind of going low for the last year, I think.
Looks that way, yeah.
Yeah. So, any questions about the life and death of stars so far?
I haven't been here for so long.
You haven't been here? All right. We're into the fun stuff. You came back for neutron stars and black holes and like that.
Good stuff.
We're right in the middle of neutron stars. Kind of like I said last night, we're actually I've incorporated last night's update in this already, since it's relevant to this material. So I'm all neutron stars all the time. But neutron stars are basically absolutely gigantic atomic nuclei. They're a mile or so in size, give or take, and 10 kilometers. And they, pressure pulled the door open. Or ghosts, maybe it could be ghosts. But they give us really interesting extreme states of matter to consider. And we get some of the best timekeepers in the universe are neutron stars. As they spin, they have a very powerful magnetic field often, and they'll have streams of particles shooting out the north and south poles, and that can sweep Earth many times a second. And there can be little settlings of the material on the neutron star. They're called star quakes or neutron star quakes, as the little parts of the crust settle just the width of an atom or two, and that actually changes the time it takes the body to spin, and we can detect these little speed ups. It's really amazing. But gravity in this extreme end of a star jams the electrons into the into the protons, creating neutrons. And so for the most part, we have nothing but neutrons here. What's actually happening, what kind of materials at the crust of a neutron star, where the pressures are lower, is all to just be discovered someday. But
So this is one stage before you get to a black hole.
yeah, this is
The neutrons are not there anymore.
correct. Yeah.
Okay.
Buddy, stay over there. Stay over there in the corner. Not right now. All right, so these are predicted in 1932 by Russian physicist Lev Landau. And like any of these predictions, nobody believed that this could actually exist until we started seeing anomalous phenomena out in the universe like this. So a sugar cube size sample of a neutron star material would weigh 100 million tons. So it's like the Rocky Mountains, or a portion of the Rocky Mountains are into a sugar cube. These things form very hot at first, millions of degrees, and over the distant future of the universe, these things will cool down to relatively cold temperatures eventually, but it's going to take a while.
So what makes them collapse? I mean, there are only a few solar masses. They're not very large.
Not very large.
But they're cooling down. That's basically why they collapse.
No, they collapse due to gravity immediately, and then the cooling just occurs over time. So they're millions of degrees throughout from crust down, so they give off light way up in the ultraviolet and beyond part of the spectrum, with radiation down into the blue end of the spectrum visibly.
So the heat is not enough to overcome the gravity.
Correct. Yeah. This is the end of the star. What's happened with the star, as we went in the previous presentations, is that the star goes through as many stages of nucleosynthesis as it can to keep puffed up, basically, to get the internal pressure needed to counter gravity. But eventually it reaches the limit to what that mass star can fuse. And when that happens, it gets to that point, then it collapses downward. With our sun, it's not big enough to create a neutron star. It'll puff off its outer atmosphere and collapse down to a white dwarf, which is a much less dense, but it's still unbelievably dense state of matter. those cool over a very long period of time as well. But in this case, you've probably gone to iron. Iron is endothermic, so you don't get support from nuclear combination in the core of a star when iron starts being created. So the core seems to turn off, the upper parts of the star fall, and you get a tremendous rebound bounce off of this ever increasingly dense core, and you get a supernova. This stuff blasts off into space, and what's left, if the mass is correct, is a neutron star. And so a bunch of material is blasted off into space, but it's not enough to go over the gravitational threshold toward a black hole, which we'll talk about next. So you're in this interesting in-between state where the nuclear forces are still strong enough to overcome gravity. Gravity can't win quite yet.
So does a supernova always create a neutron star, or is it only just certain?
Always a neutron star or a black hole. Yeah, depending on the initial mass. Yeah.
And if there are, like, earlier this year or last year, there were 2 neutron stars that collided, made dual stars or binary star system that both went supernova?
At some point, yep. Much further back, yeah. And they were close enough that the 2 remains then continue to spiral downward. So it took a long time. So these must have formed really early on. They must have been large stars, so they lived short lives. They formed early in that galaxy's formation, finished all the main sequence life, and have spent a long time as neutron stars radiating energy outward. So you had gravitational waves taking away energy from the system, and they got closer and closer and closer. And then we saw, and I'm going to talk about that next, I inserted those slides here, that process was very short in the end, not seconds, but yeah. So because you have material, whenever you have material falling together, you're going to get a conservation of angular momentum. So as the object gets smaller, it's going to spin faster. So anytime you get material collapsing down, yes, sir. I'm talking right now. How can you sit right here? Sit right here. I'm talking right now. Hopefully this works today. But you'll get conservation of angular momentum, so these things spin very rapidly at first. Very powerful magnetic fields, 10 million times stronger than the sun's, and you get jets of energy that pour out the north and south magnetic poles. So how heavy can these neutron stars get? Heavy stars, really big ones, collapse into black holes. Middle range mass stars, about 8 to 25 solar masses, collapse into neutron star. The exact boundaries of this we're still figuring out, but this is the theory, and so far our theories on the, as you'll see in just a moment, on the masses of these things are pretty good. We using what we understand of quantum mechanics and the nature of matter and gravity and the forces, we have pretty good estimates here. So this is sort of the range. Previous estimates were that neutron stars couldn't weigh more than 2.5 solar masses. Like I said last night, the core would be so dense then that the speed of sound would exceed the speed of light. So that's a limit to what it can do, because you can't have you're going to have sound. You can't have anything go faster than the speed of light. And we found neutron stars going up to 2.01 solar masses in the wild. So where was the actual limit of the resulting neutron star? So from last night's update, these 2 merging neutron stars did not immediately form a black hole. That conservation of angular momentum again held the material temporarily suspended above the neutron star, and the object that formed was 2.73 solar masses in size. We had a gamma ray burst, a lot of material thrown out, a couple tenths of solar masses, and then just seconds later the black hole formed. So this little window and the amount of light and matter that was removed gave us the best number of about 2.2 solar masses. This is about the biggest the neutron star can hold up before it collapses into a black hole. Brandon, you need to sit down. Go over there or sit down here. Quit running. So 2.17 solar masses is what one team targets as probably the actual number, but we need more data. We need more of these neutron star mergers to occur. So we get the merger, and if it's above 2.2, it eventually goes into a black hole. But if it's spinning fast enough, there's a little bit of time that it'll remain an oversized neutron star before collapsing in. If it's spinning, eventually it'll lose its spin, and the density increases as the spin goes, but the spin is radiated or lost by a much slower process. So rapidly spinning neutron stars can be a little heavier, a little larger than they would be, so a little less dense. So the lighthouse model is, no sir, you gotta sit down right there. Is where we get pulsars, and they were originally called LGMs, which was short for little green men, because they thought this may be the first sign that we had of intelligent life in the universe. So we didn't have a accepted, no, sit down in a chair, sir, mechanism for how you could get a regular signal from space. So maybe this was a timing system of some kind. We saw things as rotating so fast that we're getting a pulse every 0.033, so 3/100ths of a second, up to much slower at 3 3/4 seconds. Get these little slight increases from quakes on the surface. The fastest recorded, and I haven't found anything faster yet, is 642 rotations a second. That's a very newly formed one. That's 40,000 kilometers per second. So this one is artificially less dense in its core. It's going to be almost flattened. It's rotating so rapidly. Anything faster probably would start throwing material off, like our oversized neutron star merger did. This is an extreme state of matter. So we can get pulsars that are fueled by a partner star. So you have a star that's swelling up. It's entering the later stages of its life. It's starting to burn the next materials up in its core. And so its size is such that the outer atmosphere now is passed over that seesaw point between the two objects gravitationally. So the center of gravity of the system is underneath the surface of this now puffed up giant star. So it starts to lose matter onto the neutron star, and that can really fuel these high-powered X-ray beams out the magnetic poles. Magnetic poles, just like the Earth right now, do not have to be aligned with the rotational axis of the object itself. They can be almost any direction conceivable. So the closer to the equator they are, the more sweeping action you're going to get across the universe. You're going to get more travel. Just sit there and be quiet. Be quiet right there. So the material that falls off the star can build up on an accretion disk and eventually detonate. And so you can get nova phenomena from this. You'll get fusion occurring in the hydrogen above the surface of the neutron star and in the inside edge of this accretion disk, but it's not in the middle of a star. So the energy just blasts outward from there. And again, these are really intense. If we had one of these go off, even in the nearest 10% of our galaxy from us, it would clean off life. It's okay. Go take it to the trash. On the Earth, it would just bake us in high energy radiation. So this is just like a lighthouse. As it rotates, its beams are. Okay, Brent, you gotta quit talking. Sit down. We're not gonna do this again. All right, so any neutron star questions?
So the only way we see the beam and we see the effects is when the beam sweeps.
It's got to be aligned with Earth.
So we
Yeah.
only see a fraction, a small fraction.
Absolutely, yep. Here's a little example of the timings and intensity of the shots of radiation coming towards this little lighthouse model. All right, let's get to the real fun now. We'll go to black holes. So if the stars is even larger and the stellar remain in the core is bigger, the nuclear forces are not enough to hold the star up. Brandon? Okay, why don't you go back and watch your movie. I got a movie for you. Go back in the corner, sir. So here's an animation of the distortion of space around a black hole. The camera's moving around or maybe orbiting the black hole. And the distant galaxy in the background's light is passing through this area of space that is intensely bent by just gravity. And gravity is a warping of space-time. And this is a numerical model of what that would look like. We have not done this directly, but we have seen evidence of this happening off in the distance. There's an artist's rendition of a black hole with its with material falling into it, forming an accretion disk, a really hot region near the black hole, giving off a lot of radiation, but it's obscured in the plane of rotation of the system. And then out the north and south poles, you've got a lot of energy spewing off, accelerated by the black hole and the magnetic fields around it. That's another picture of the warping of space-time. This is from the movie, is it, oh gosh, what was it? The movie escapes my head right now. It's.
We just watched.
Oh, the galaxy?
Yeah, the one with the black hole, and there's a recent one.
Yeah, can't remember.
It's not Gravity. That was. I know, it's just gone from my head. Sorry, so people watching out there, you can Google this recent film. But it'll come to me probably. So this is a frame from the film, and this is using general relativity equations to a resolution that no one had done before. And it's using all the graphical calculation power of a special effects studio. Brandon, stop. Stop moving chairs around. Go watch your movie.
So that center line is moving through that?
Yeah, this is the accretion disk here. And then the light all around here is the accretion disk on the back side. So the light from the back side is being warped around to approach your view from here. So this is all one continuous disk. You get to see it all around the black hole.
In the last few slides, the circular black hole back again,
Yeah.
or again, passed through the line.
Yeah, here there's no accretion disk, so it's just the stars from behind.
But the one behind it, next one back, that one. So what's it passing through right there? It's not
That's a much more distant galaxy. So you're way off in the distance looking at a black hole, and beyond the black hole is a galaxy even further out. So you're looking through a telescope in this simulation to see the warping. And theoretically, the black holes are moving through space, and you've got very distant galaxies. So if you're here looking across our galaxy, and you could get a black hole pass in front of a much more distant galaxy in a short period of time. And so you would see this kind of effect. So this light signal is something that you could pick up.
It would be interesting if they had done that movie without, instead of having an edge on galaxy, have a face on galaxy.
That's true.
That would
makes it denser. So the whole idea behind a black hole is the escape velocity of the black hole, or the escape velocity of any object with gravity. That depending on the strength of gravity at the surface or near the surface, you've got to achieve a certain speed to get free of it, to go as far out into the universe as you want. And from Earth, we have to get up to 11 kilometers a second, 25,000 miles per hour. As your starting point is in a weaker portion of the gravitational field, so more distant from the center of an object, say here's a 1,000-mile tall tower, then it decreases to 8.8 kilometers per second. You only have to get up to 20,000 miles per hour. So as a space shuttle or an Atlas rocket or something takes off, it's escaping, and gravity can be slowing it down, but it doesn't have to be going the same speed as it was at the beginning to escape Earth. But once you get enough material jammed into an object, there's a point in which you've got to exceed the speed of light to get away from the object. And that's the black hole. That's where the black part comes from, is that light cannot get out. As we'll see, there's more to it than that, because in a gravitational field, time is slowed down. So time is slower here than it is at the top of the atmosphere, than it is out at the orbit of the moon and beyond. So time on a black hole is slowing as you get in till you get to the event horizon. At the event horizon, the escape velocity is the speed of light, and time is also stopped. So without time passing, you also don't have the ability to escape. You have no time. So one of the early models of a black hole was figured out by Schwarzschild. A very massive object with a star core greater than 3 solar masses keeps collapsing. You form a singularity in the center. This is where all the matter resides. We don't exactly know that for sure.
Well, it's the asymptotical maximum or minimum, right? I mean, in a math equation, you go down to the infinity.
Infinity, right. Right, you've got infinite density at the singularity, right. We don't know that for sure.
It's a theoretical point.
Right, well, and from our point of view, it never occurs. Because from outside, and the point of view matters a lot with black holes, outside the event horizon, time stops here, so the black hole never forms from our point of view. If you fall in to the black hole, you don't encounter the event horizon. If it's a small one, we'll talk about the problems with tidal forces in just a moment. But if it's a very, very large black hole, the tidal forces are not very great. You just keep going, and you get to see the black hole form as you fall into your doom, as you disappear from the universe. So again, point of view matters a lot.
That's
It's a great burial.
It is a great burial. That would be a cool way to go. Yeah, so if you have to pick. So the Schwarzschild radius is a pretty simple little equation here with Newton's gravitational constant, mass of the object, speed of light squared. If you have a 10 solar mass star, then the event horizon is 30 kilometers radius. Our sun, if it could be artificially squeezed into a black hole, which it can't, it's not big enough, would be 3 kilometers in radius. The Earth, if you could put it into a black hole making machine, would be 9/10 of a centimeter, so about like that big, the entire Earth. Event horizon there with its matter, a point in the center. That's really hard to get your brain around, that there is no limit at the bottom once the nuclear forces can't sustain things. So our cartoon example is taking a rubber sheet, and if you plop a black hole down in there, you get an event horizon at the point of no return, somewhere down in the throat, and this extends infinitely far. And of course, in physics, if you really want to discover things and push things to the limit, you want to see what your equations and what your physics do at a black hole. So ultimately, almost every theory gets pushed that far, but we don't have a theory for quantum gravity. We don't really know what gravity does in this extreme environment. And so that is a huge portion of what physics is working on today, is trying to overcome that ignorance. One of the questions I like to throw at my students is, in fact, we're doing orbits right now in one of my classes, and one of the questions out there is, I put out, is what would happen if the sun turns into a black hole? And most people's answer, just general public answer, is the black hole will suck the Earth in. Like, black holes reach out and suck everything in. But if you use my magical black hole making machine and did that on the sun, you still have one solar mass there. And already Newton's equations show that you can treat a gravitational field as if all the matter is in the center. So tidal forces are what you get from the extension of the object. So the size of the Earth, the size of the moon, the size of the sun is what gives us the tides and tidal torquing of the bodies nearby. So all it would be is the solar system goes dark. Everything just keeps on turning the way it is. We go around the black hole in the center once a year and freeze up solid. So how do we find these black holes? Well, we could look for gravitational lensing events, those points, moments where, or short periods of time where light flares from some place, where the light of a more distant galaxy is amplified, like that earlier animation. Or we can look for black holes that are in the fortuitous situation of orbiting another star that we can still see. Either the star is visible and we can see its motion moving back and forth in space, or we can see the Doppler shifting of the light from the star as it moves around something that we can't see. Or if we have a situation like I described earlier with the star expanding to the point where material is falling past the pivot point and forming the accretion disk, even if we can't see that, we can see maybe the jets, we can see X-rays coming off, we can see something coming from the system that a normal star would not produce, that the violence around the accretion disk is creating. We have about 150 black hole candidates now. We know of at least 2 binary black holes and a trinary black hole system. And our first one that we discovered, I'll get back to that in a moment, is Cygnus X1. It's right here in the neck of the swan. There's Cygnus over there on the wall. So the black hole's right, let's see, it's right there. And that's a binary system where you have an X-ray source. So it is X1 for X-ray source 1. So once we first started looking, every time you develop a new type of astronomy, you make fantastic discoveries. And the high energy astronomy world is no exception and critical now to these discoveries. Here's source X3, Large Magellanic Cloud, X3 in the constellation Dorado. Another one in Cygnus, Vulpecula, Scorpius.
So looking at Cygnus, you would not see.
No.
You have to detect it with X-rays.
Right. And then later we found the blue giant partner of the X-ray source. Yep. Yeah, there it is. There's an O supergiant.
With the star, I guess, sloughing off material into an accretion disk of the black hole, you could see that.
Mm-hmm.
I mean, visible light would be.
Yeah, I mean, you got an O supergiant, and you've got, so you already have a lot of the highest energy radiation put out in the optical and ultraviolet that a star puts out. This is just being then heated up further from ultraviolet to X-rays and like that. So yeah, there's probably a continuum, but the strongest source is going to be the X-rays from near the black hole and the ultraviolet source in the far blue from the O giant star. And the in-between stuff, as it ramps up, would probably be a lot dimmer, yeah. But it would be a continuum, yeah. And so eventually that thing is going to go and presumably make a black hole too. So this will eventually be a black hole system. Just the one that is a black hole now was even larger. So its life ended sooner than its companion.
And this is in the direction of our center of our galaxy.
Well, that's down towards, yes, it's maybe a quarter of the way across, because the center of the galaxy is right about there. Yeah, so not too far. So falling into the black hole, you get time dilation. Like I said, time runs slower. So you're out here, you watch 50 minutes go by as you orbit. You have your friend back down towards the black hole, firing engines to keep from falling in. And in the time 50 minutes goes by out here at this arbitrary point, 15 minutes only has gone by. That's a lot of fuel you're burning there, though, to be fighting. This is just an orbit. Orbits don't take any additional energy. You can orbit a black hole safely. So you also get gravitational redshift, that the light escaping from near here has to work its way out. So in the same way that you get a redshift from, say, the expansion of the universe, as we'll talk about in the next section, you're getting redshifting from light escaping the vicinity of a black hole. So the X-rays you see from in there probably were gamma rays, or the high-end gamma rays, but they've been redshifted toward the X-rays as they leave that vicinity. For small black holes, you have very serious tidal forces, very large. The galactic black holes in the center of a galaxy have a very gentle curvature at their event horizon because they are so large, and so the tidal forces are much less. So you could actually sort of enjoy your one time only vacation into a black hole in a galactic black hole, but here on a smaller one you would get spaghettified. So as you get closer, eventually the gravitational force on your feet are a few pounds more than your head, and 100 pounds more than your head, and 1,000 pounds more than your head, then 1,000,000 pounds more than your head, and eventually gravity itself pulls all the tissues apart, then all the molecules apart, and like that. So it's spaghettification. That is a technical term. So there's the Cygnus X1 artist conception. You've got the swelling O star. It's probably heading off the main sequence now. It'd be great to see that thing blow, but I don't think that's happening in the near future. And then you got the material falling down. You got a hot spot where the material falls onto the accretion disk, and the accretion disk gets hotter and hotter and hotter inward, but then you have more redshifting as you get closer to the black hole itself. Black hole research. We will talk about this more in the nature of space and time in the next section, but when you have, I don't know if I want to get too far into that, but if you have a light source away from a black hole, you have a little wave front of the light escaping this event. So you go flash bulb or iPhone flash, and you take a picture. Away from the black hole, you get a nice circular event spreading out. So people in all the directions around this bulb will see the flash at the same time. If you have a flash event go off near the event horizon, then you do have some event head outward, but the stuff off to the sides gets more severely redshifted, and then the light this direction falls down, never to be seen again. If the light event happens inside the event horizon, then the flash actually travels away from that event point and remains trapped inside the black hole, so it never comes out. And what we have in empty space, and we'll talk about this again more in the next section, is empty space itself is not really empty. In fact, I gave a talk on nothing last year. And empty space itself has little virtual particles appearing. They're particle-antiparticle pairs, and they get as far apart from each other as they want, but they have to recombine and annihilate each other before they can be detected directly. And this is due to Heisenberg's uncertainty principle. So you got these little particles doing this all the time, and that really is an important part of how the universe functions. And we can measure it as what's called a Casimir effect. You take two plates, put them really close together in a vacuum, and you'll get a net pressure inward, because these little particles are coming and going in random directions all through space. If you close the plates together enough, you limit the direction that these particles can move. They can't go side to side between the plates. So you've now limited their degree of freedom, but on the outside of the plate, they can go in every direction. So you get a net inward pushing from these particles. And the actual functioning of atoms and everything like that come about with these little virtual particles. What's interesting is that the event horizon, a particle is created, you pair creation out of nothing, and the event horizon itself is in the way of one of the particles. Down goes one, and the other one escapes. And this discovery is Hawking radiation. So this is one of his big contributions to science. And that event horizons lose energy this way, that you get a net outward energy that's positive, and the energy going inward takes away from the energy budget of the black hole. So black holes are all trying to evaporate, but this temperature is basically what it looks like, is based on the size of the black hole. So very, very large black holes are very, 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 very cold, just a millionth of a degree above absolute zero. Smaller black holes would be warmer, only a thousandth or so degree above absolute zero. The universe itself is still 2.7 degrees. So the universe is much hotter than all black holes that we know of and expect to be out there. So all black holes are still getting a net input of just energy from the Big Bang that swamps the Hawking radiation. I just was watching on Netflix the new Lost in Space reboot, and a black hole figures into the plot line. I won't spoil it for you, but they do get all concerned about the Hawking radiation that they detect over there by their star. Like, it just drives me crazy. So. Now, related to this, and we'll talk about this more later, that we don't know where information goes. Is the information lost going into a black hole? Because at the real basics of what space-time and physics and energy is information. And so, if you throw a couch into a black hole, because the thing's got bed bugs or something, can you, or some future highly advanced alien race, reconstruct what fell into the black hole by putting a big observation bubble around the black hole and observing all the radiation that comes out of it over all time, and somehow, unbelievably, reconstruct it. This would be a lot harder than taking a book and putting it into a fire, burning up to ash, letting the smoke go, collecting the smoke and reconstructing the book. A lot harder than that. But in theory, can you do that? Or is the information completely lost? And Hawking had a bet with another physicist as to whether that would occur. And when you really get into quantum mechanics, you realize that if information can be lost or destroyed in a black hole, that the theory of quantum mechanics comes unraveled. So our understanding is it really shouldn't. And Hawking did concede later in life that the information does come back out through this Hawking radiation. One of the problems with this information, though, is something called the information paradox, that particles can be entangled with each other. When you ever have a nuclear process occur, you can get two particles created, one spinning up, one spinning down, and as long as nothing interferes with the system, you can separate these little two things apart. If you observe this particle over here and see what its spin is, you know instantly, no matter how far away that particle is, it's got the opposite spin. And there's a lot of different experiments one can do. They've done this with fiber optics over great distances on Earth. When you really get into playing with it, though, it's possible that a particle the particle can become entangled with its past self and its future self. Now, quantum mechanics does not allow double billing. You can't double entangle a particle with itself through time. But yet, this process of material falling beyond the event horizon and being re-emitted would allow that to happen. And that's one of the great headaches right now for physicists. They have created the concept of a firewall, that there is a physical mechanism that keeps particles from entangling with other versions of themselves. And it remains to be seen whether this black hole firewall is really the correct physical solution, or if there's something else going on that we don't understand. Again, we don't have a theory of gravity that works with quantum mechanics. And so a lot of these headaches that we get probably arise from that ignorance. That we just need to figure this out, and we just don't have it done yet. There is also work that we may not always get a neutron, black hole after a neutron star. If you get a very slow collapse, the Pauli exclusion principle, this is another quantum mechanical effect, keeps two particles from occupying the same point in space. And so you may get unusual neutron stars that can stay neutron stars longer than the physics allows. So maybe the window between 2.01 and 2.19 or 17, whatever it was, maybe an interesting region where you're dealing with quantum mechanical effects in neutron stars that we have yet to really figure out. So there's some stuff yet to figure out in quantum mechanics. Probably not, but it's possible. You might get an in-between state where you get quark stars, or Brandon, quick kicking. So you might get stars made of strange particles. This is not weird. These are strange type quarks. You might get gluon stars, boson stars. It's almost a black hole, but if it goes slow enough, it may stop in a state more squished and smaller, higher density than you would get with just neutron stars, but it hasn't fallen off the cliff yet. We don't know that, we haven't observed that, we don't exactly know what we would see on the outside that would be different, at least from a distance with our current technology, nothing probably. But
This is basically all mathematics. Right?
these are all mathematics, possibility in
mathematics.
in between states, between neutron star. Yep. A Q ball or Q star would be even denser state. So black stars is a term used for these. So they've gone beyond neutron stars. They're not black holes yet, but we don't know.
Dark matter.
Well, it's not dark matter, but that's a different thing. So I don't want to get into that. Other possibilities with a black star is that you got slowly falling material again, so it's not as violent as a supernova explosion, but maybe you get a neutron star that you keep adding small amounts of stuff to, and rather than build an accretion disk that the novas, you can gently nudge it into a black hole state. In that case, you get, this is another idea, this black star idea, where you get a mass-filled interior with a very high temperature out to the center, but you're just enough that really not much light can get away from it because the gravitational force of the surface is almost at the event horizon level. So this would deal with vacuum polarization and repulsion that can occur at the boundary, and it's an even closer state to a black hole without quite getting to a black hole. We don't know if these can exist, but it's possible. Seen first by amateur astronomers, gamma ray bursts can have a bright optical component that only lasts a fraction of a second to a few seconds. As professional astronomers, we're doing long exposures and not noticing these things, so they were in the Bigfoot category for a while. But eventually, someone caught an image of one, got the afterglow that was visually identified with big observatories, found that it came from distant galaxies in some of the outer reaches of the universe. The light was a full spectrum blast, so it didn't have strong emission lines. These are some of the most powerful explosions in the universe. You get 10 million billion suns of energy released in a few seconds. You can outshine the energy output of the whole universe, or 10% of the universe for a moment. So that's quite an explosion. Now that is if it's radiating in every direction. If it's coming out the jets of some type of object, then that cuts down the amount of energy released by the event by a large amount. So maybe you're only outshining the universe by 0.5% of the universe, or 1/10 of the percent of the universe visibility. But still, that's a lot of energy coming from a small event.
It's more believable, then.
It is much more believable, right, that you've got a jet-like effect occurring. So here's the spectrum and afterglow of that first verification. These are thought to be maybe the collision of a couple of neutron stars or a couple of black holes, or maybe a star being ripped apart by a black hole. And since I last taught this, we have seen examples of all these. And now that we have gravitational wave observatories functioning, then we're seeing the gravitational ripples in space-time that coincide with some of these events. So yes, all of the above. But you can get a star orbiting a black hole, gets ripped apart, and blast. So there's still discoveries to be made. There are short and long gamma ray bursts, and as the high energy universe is exciting and fun to study. So that's the end of the third section of the course. We're pretty much at 11 o'clock. So let's take our 10-minute break, and we'll pick up with the universe and the large-scale universe with galaxies and...
Pick up again, or you want to go home and take it
Oh no, we can do it.
Okay.
Well, I think we're surviving well. You guys aren't too distracted? Okay. All right. Test, test, test. All right, we're back on. I didn't turn off the recording, so. All right, so large-scale universe. We've started in our backyard looking up months and months ago and seeing what we can see. We've worked our way all the way up to the stars. And what we get to do is once you figure out how planets form, then you generalize to all the planets in the universe. Once you figure out how stars form, you can go to all the other stars, how they form, live, and die in the universe. So when you get groups of stars, you have galaxies, and now we can start building that structure upward to the universe itself. So we'll get from galaxies to the theory of everything in this section. This is chapters 14, 15, 16, and 17 in the book now, so if you want to start reading ahead into the material that's come, we're in the mid-teens. All right, so here's our galaxy from the inside. This is invisible light. This is the entire sky. Here's the large and small Magellanic Clouds. Here's our galaxy. Here's the core of our galaxy in the center. You can see lots of dust. In fact, the southern side of the core of our galaxy is peeking through. The northern side is largely hidden. And as you get out into the galactic suburbs, things get dimmer and pretty dusty as well, so you don't get as much light. So this is what astronomy largely focused on, no pun intended, early on, because that's what telescopes did, and that's what our human eye did, and that's what photography was good at, was visible light. Then we started branching off. In infrared, in the same way that blue light dominates the sky in the daytime, but is scattered when the sun is going down or rising, so you get the red light only through. The redder light can get around dust particles and atmospheric constituents in the universe. It can get through the gas and dust between the stars, and you can get a much clearer view of our galaxy and beyond. So the James Webb Space Telescope going up is primarily an infrared telescope because it opens up so much more. Now, it's a longer wavelength, so the resolution that you get is not as good. So you need as big of a mirror as you possibly can get, sensitive and fine resolution detectors you can get to get that. Believe it or not, we discovered the galaxy only 200 years ago. You know, what? But yes, it was actually assumed that stars were distributed evenly through space. Now, how you can look at the Milky Way and not figure that out, that there's something going on, I don't really know. 100 years ago, the common belief was we were in the center of the disk of stars, and it wasn't discovered later because a lot of the core there is hidden by gas and dust, and people were in the northern hemisphere primarily, so that the core, bright part of the core, was kind of hidden below the horizon, already experiencing extinction from the Earth's atmosphere from the viewer's point of view. So yeah, we had a pretty goofy belief, and it also, you know, if humans can put themselves in the middle of things, we do. That's just sort of our default. Hey, look at us. We're the center. But physics, at least, repeatedly shows that we're not. every discovery, like you go to a new wavelength of light or a new type of astronomy, you make new discoveries. Every time you make a new discovery, you find out that we're not as specially positioned as humans as we thought. Let's see. So yeah, I don't need that picture. So what helped break our ignorance and show where we are in the galaxy? We're looking at variable stars. Our Lyra is the original one, Cepheid variables from the original discovered in Cephas. Henrietta Leavitt cracked this. I think I have a little more on her in just a bit. But some stars have a periodic instability in their core. So they put out energy from the core that heats up the interior of the star. Anything that heats up expands. Anything that expands gets more surface area, but the surface area cools. From Wien's law that we talked about a few months ago, the peak energy decreases, and once it puffs up, it's got more surface area, it loses the energy, the interior of the star cools, it shrinks back down, it gets smaller, but then also hotter, it puts out higher frequency light as its peak emission, and it pulses like a clock very regularly. And so we have this nice little period here that is based on the absolute magnitude of the star and the period in days, from 1/3 of a day up to 100 days on the horizontal part of the scale here. Our Lyra down here, type 2 Cephids, type 1 Cephids up here. So once you figure out the spectrum and the absolute magnitude from the spectrum, the temperature, and going backwards through the main sequence knowledge that we already have about stars, then you look at the period and you can distinguish type 1 to type 2 or a low-end type 2 from a high-end R Lyra. And you now know from the pulsing how bright this star actually is. If you know how bright it really is intrinsically, then you can see how bright it looks and do the calculation from the magnitude to how far away it is. Once you have its distance, then you can map out those regions of space. So other stars that are the same or similar sequence in that vicinity but aren't pulsing, you now know their distance. And you can start mapping your way further and further out. These are quite bright stars, which also helps. So they are visible as individual stars all the way into other galaxies, nearby galaxies. So what we've pieced together over time, this is an early picture, a mental picture of what our galaxy looks like. This is not accurate, but you've got spiral arms, you've got a nuclear bulge off to the side, you've got some little material around in a halo, and in there you've got globular clusters, which are nodules of stars. There's a globular cluster right here. This is an open cluster. So open clusters are primarily in the disk, primarily, and globular clusters are in this big halo region, all with their own orbit around the center of a galaxy. So another artist's picture here. We have more of a barred spiral than this picture shows. I think I might have that, but our location is about 28,000 light years from the center of the galaxy. So we're out in the galactic suburbs. There's more galaxy beyond, but not too much more. The entire galaxy is roughly 150,000 light years across. So depending on where you stop counting material that's out here. 100,000 light years. So if you get a galactic civilization, as many science fiction books like to do, how do you get them to communicate? Because it takes 200,000 years to get a message from there to there and back, an answer back, far beyond the length of all of human history by, what, 10, 20 times? So, yeah, so that's, the speed of light is really slow, is what, I mean, it is crawlingly slow. Our universe is very large, yeah, absolutely. So in the galactic plane, stars pretty much obey a nice little circular-ish orbit. Halo stars have their own almost cometary, if you think back to the solar system scale stuff, of going above and below the plane and doing their own thing. But once you find stars in the disk, stars in the halo, in the orbits that they have, you can use Kepler's law to figure out the mass of the galaxy. So you can do the same thing that you do inside our solar system to figure out how heavy the sun is and how heavy Jupiter is, and Jupiter from its moons and how big the moons are. You can work your way out because we know how to figure out stellar masses, and we can build everything up in piece from what's nearby and measurable up to the vast stuff that's otherwise immeasurable. Stars in the plane can ride up and down almost like I was going to say horsey at the grocery store, but he'll get excited. He'll want to know where it is. And there are some researchers who say that, or I think right now the sun is above the disk, but we should pass down through the disk somewhat higher density material. So there may be some climatic effects on the Earth, or effects on the solar system, perturbations of comets and things like that. I don't think that's proven. It's just one of the theories rolling out there that as we ride up and down, our passage through the denser part of the galaxy may have some effect. If I recall, I think it takes 25,000 years to go around. 250? Yeah, okay. I couldn't decide between the two. Yeah, 250,000 years to do one orbit around the galaxy in our up and down ride there. Thank you.
Not in our lifetime.
It's not happening in our lifetime, no. Again, 25 times longer than human civilization. So we expect Kepler's motion, but that's not what we find. And this opens up a whole can of worms in astronomy that out in the outer reaches of the galaxy, part way out and all the way the rest of the way, things are going too fast. Why don't they fly away? They have the tangential velocity great enough to escape the gravitational pull from the mass of the galaxy, and yet they don't. They continue in a nice tight orbits, and this opens up dark matter as one of the models to explain why this is occurring. The reason it's called dark is that it's theorized to be a form of matter that doesn't react with electromagnetic forces. It may, some of the candidates may react with a weak nuclear force. So you have what are called WIMPs, weakly interacting massive particles. Or maybe they only interact with gravity. So it's a theorized different type of particle. If you think of it this way, electrons don't care about the strong and the weak nuclear force. Who cares? They care about electromagnetism. They work with photons as the force transfer particle. But neutrons and protons definitely do care about the strong and the weak nuclear force. They are particles that work with those additional forces. So to make this work, to explain how our galaxy holds itself together as it rotates, you have to kind of visualize a halo around the galaxy, possibly going 7 to 10 times further out than the visible radius of the galaxy itself, and contain 10 to, in some galaxies, 100 times the mass of that visible portion of the galaxy, the stuff that's made of stars and dust and gas that's reflecting starlight or absorbing starlight and re-emitting it in infrared or something like that. So because it doesn't interact with electromagnetism, light goes right past it. Now, it's got mass, so it's going to warp space-time like any mass would. So light has to take a curved path through it, but that's different than interacting with it directly. Like gas and dust either reflect or absorb or emit light. So
Is it something similar to a Higgs boson? It gives particles, protons, their mass, basically?
yeah.
Right, I mean, basically a jello-like substance or whatever that things fly through?
Yeah, and we know the Higgs boson isn't dark matter, but that is an idea. It's another particle that has its own aspects of how it interacts with reality.
You can see through it as well.
Right. Yeah. And of course, when you get into quantum mechanics, anything as a particle is also a field. So you have a Higgs field along with a Higgs particle. You would have a dark matter field along with. You have electromagnetic field as well as photon particles. Everything is a particle or a field depending on how you play with things. So here's a artist's picture of what a dark matter halo would extend, say, around our galaxy. There's our galaxy, there's a central bulge, there's a halo of globular clusters and maybe even satellite galaxies that our galaxy is gobbling up or tearing apart or in orbit around. And then you've got way out here this giant tenuous bubble of dark matter. So here's rotation, so you're looking at the orbit of stars around this other galaxy. We can measure this again with using the Doppler effect. And you can see the stuff inside going quicker than out here, suddenly boom, it just becomes linear. So you've got a orbital velocity that we just wouldn't expect out here. It's just the fact that it goes straight makes it act much more like a record or a CD or DVD than an item made of all these individual particles just orbiting. So how do we get galaxies? Well, the galaxy formation, yes?
Well, maybe now, maybe later.
Yes?
But if you get two galaxies colliding,
Yeah.
how does dark matter then interact?
We have one example, famous example called the Bullet galaxy. It's two galaxies that did collide. Their visible matter creating portions interacted and have started combine into a hybrid object. But looking at the distortion of space-time caused by the gravity of the dark matter, we got two clouds of dark matter that are continuing on out beyond. So I don't know if I have that. I should probably add that. Yeah, so the Bullet galaxy is an example where the dark matter didn't interact, so it didn't stay in the fray of the galaxies colliding. It's out as two separate entities that used to be around the center of mass of the original object.
So then there's no galaxy formed. After the two merge, basically everything flies away.
Right. I think eventually gravity wins. I mean, eventually it will slow. The entire system has a center of gravity, and that gravity is going to bring this stuff back. There's some ideas about, or thoughts about, that we wonder about what dark matter role it played in the early universe in star formation. That early stars may have been a higher concentration of dark matter because the universe is smaller. So dark matter was much more concentrated, as was normal matter. And so there's thoughts about what that did that, or whether we have dark matter pooling in the center of our Earth and pooling in the center of our sun, and what that does. Because if it's not going too fast, then it's just going to settle down in the local gravitational wells at the bottom. And it can drift right through the sun and go down to the core and sit there. It doesn't care about electromagnetism and density and heat and things like that. It's a different, dark matter is a different creature. We're just used to this world of baryonic matter and fermionic stuff. So how galaxies form, we go to the same general model as we had for solar system formation. Dark matter, of course, is going to play a role in this. And dark matter seems to have helped trigger the big strands of galaxy formation that we see around the universe. We'll see that as we get to the larger scale structure of the universe. From the oldest open clusters, we have an age of about 7 billion years for our galaxy. Looking at the globular clusters, we have an age of about 11 billion years. So the universe being just under 14 means our galaxy started getting its act together pretty early on in the age of the universe. Stars in the disk have metals. That's everything heavier than hydrogen and helium. But the stars in the halo are almost entirely hydrogen and helium. So they're closer to first generation stars than all the stuff that's been reworked and exploded and reformed and new stuff formed, all happening in the disk of the galaxy. But the general idea is you get this big region of more gas and dust than every place around, and it starts to collapse gravitationally. Maybe a black hole forms in the center, and there's going to be some preferred motion of the stuff that then concentrates and is conserved through angular momentum. All the other directions of rotation cancel out. You get one overall rotational axis and direction for the material. It can, of course, there's no up and down in the universe, so they can be any direction they happen to go, but they do get a rotational preferred axis. So thought is if you have a high density protogalaxy cooled faster, you end up with an elliptical galaxy. If you have a lower density early galaxy and it cools slower, has time to flatten out into a disk, and you get a spiral galaxy. There's been proposed models where more dark matter aids in the spiral galaxy's formation, less dark matter, an elliptical galaxy, but I think there's observations that show that those are violated also. So there's examples of elliptical galaxies that seem to have a good amount of dark matter as well. So, we are out in the Orion Cygnus arm. So if you look at, let's go back over here to Cygnus again. So looking at Cygnus there and Orion here, the stars in those sections you're looking into the arm as a cross section. So the Milky Way that's there and the Milky Way near Orion are right in. You can even see the overall U shape here of additional stars, and this is the arc of our Milky Way galaxy all the way along, and people on the camera don't get to see that, so sorry. The center of our galaxy is towards Sagittarius, so again it's along the Milky Way, but the Sagittarius is right down here by the wall plug. And looking at radio observations, we can get additional density regions mapped out. Here's the galaxy center here. We can't see easily beyond the galactic center because it's so dense and dusty and crowded and noisy down here in the center, so we have a blind spot there. The Orion Cygnus arm arcs right through here with the sun sort of on the inside edge of it, with the north pole of the galaxy pointing upward. It's not too far off of the north pole of the Earth. Then what's coming towards us, or the direction that we're leaving, is Cygnus, and we're heading towards the direction of Orion. I believe that's correct. So in from us is the Sagittarius arm, and out from us is the Perseus arm. You can see there's still stuff between the arms, but we've got a lot of brighter stars right in there. That's a fairly good picture of another galaxy that might look like ours. I think more recent observations have more of a bar in the middle. I don't know why I've always not liked barred spirals, but I've not wanted our galaxy to be a barred spiral. I like the more symmetrical, circular ones, but I don't think the data supports that. So what I want doesn't seem to matter in galaxy formation. So what makes these arms? Well, these are density waves traveling through a fairly uniform disk of material. And so as the density waves travel around, it's kind of like big sound waves or shock waves traveling around, they help trigger clouds of gas and dust to start collapsing. And the stars that form the fastest and shine the brightest are the O and the B type stars at the hot end of the spectrum. It's going to be still very cold, sir. And so, again, just like Hollywood stars, we see the big bright ones more, and we think that's what dominates everything. But the amount of material in between is pretty much the same. These just stand out visibly because of all the new, bright, short-lived stars. So you got lots of dimmer stars that are formed by this collapse too, but they're so dim that they just fade in the background and are not as noticeable. Similar to, so here's one density wave here, here's another density wave, and it's fairly independent of the orbits of these things. So it's not like the arms are solid things sweeping around the galaxy. Our galaxy center, the nucleus, again, is right above Sagittarius. If you look at Sagittarius right down here, you look at, you got the little teapot right there, and look where the spout of the teapot is and go right above the spout where the steam first is coming out. That's the approximate center of our galaxy. It's about the dense star-choked area is about the angular size of the moon. Down there, about 1/2 degree or more. We have a massive black hole down there, 2.7 million solar masses in the center. Stars, we've observed only 860 astronomical units away from the core circle in about 16 years. The event horizon, the short child radius we talked about earlier, is about 13 times larger than our sun in size. So it's a very small object still. Now the Schwarzschild radius is a very simple model. If you get a rapidly rotating black hole with a strong charge, other more complex things happen, but don't worry about that. Here's a sequence of images going from visible to infrared where we zoom in and zoom in and zoom in down to what look like jets of material or maybe infalling strands of material towards the black hole in the core. So it's a little teeny area here blown up. It's in, pretty sure it's a radio observation. So there's the central region of our galaxy. In infrared, Sagittarius A, and the black hole itself is denoted as Sagittarius A star with little asterisks. We are working, there's a project underway right now called the Event Horizon Telescope. I think they've collected all their data last year, and they're working on putting it all together to create the first image, direct image of the event horizon region around the black hole. They also are looking at M87, which is the next largest black hole event horizon in angular size visible from Earth. And I've put all the data on the hard drives, they've brought it all together, and they're working on processing it through. But they use a global-sized network of radio telescopes. The bigger the telescope, then you get to, just as we talked about in the telescope section, it's an interferometer, so you combine all the information, and it acts like a telescope that has that size of the Earth, the face of the Earth itself. making the measurements, putting together. What will we see? Will we just see noise? Will we see an event horizon like this or like this with a hot spot if the accretion disk is tilted one way or the other around? Or will we just see some weird pattern distorted by a torn up space-time? We don't know. But here's the picture of the telescopes across the Earth all making observations at the same time. What we expect is something kind of interesting like this. So we hope. But all that is a mathematical simulation at this point, so stay tuned. I'm sure that will be a news update that I bring when that information is released. All right, so we'll take our galaxy, we'll leave and go out and look out all the galaxies around us. And it's so funny that even in books of the early 1900s called these things nebula. You had the Andromeda Nebula. Was the way it was described in the textbooks, because we didn't know that they were extragalactic things. Our galaxy was it. So we have elliptical galaxies are one kind, like I said earlier. You have spiral galaxies, you have barred spirals, you've got irregular galaxies like this one. And you have interacting galaxies that are coming in gravitational interaction with each other. We have the Andromeda Galaxy on its way here. It'll be here in about 5.5 billion years. And astronomers have already named the resulting merger of the two Milkomedia, from Milky Way and Andromeda, so maybe Milkomeda or something like that. I think humanity in 5 billion years, if any version of it still exists, will probably come up with their own name, and I don't think they're going to care about us. So let's go through a time here. A survey of galaxy types. Here's an interesting little critter. It's like an elliptical with a big dusty ring around it. So you don't really have a... Oh, thank you. You don't have spiral arms per se, but you do have a dusty disk with a giant central nucleus. And here you have a nice open spiral, lots of little arm detail, bit of a bar across the middle there. There's one a little dustier, a little denser. Still, you got spiral arms, but lots of other material in there. There's a nice nucleus, kind of tilted towards us somewhat. Edge-on galaxy with the dusty material down its lane. Kind of how our galaxy looks like to us from inside out in the edge of the galactic suburb. Here's one with a good bright nucleus here. General haziness of stars, but this dusty disk inside, not very, very tenuous. Oh, elliptica. Oh, gotta love PowerPoint sometimes. So nice elliptical galaxy here. It has satellite galaxies too. Galaxies are voracious eaters, and we know that our galaxy has eaten a number of smaller galaxies over time. It's like the yo mama jokes. Your mama's so big she's got other mamas in orbit around her. So our galaxy is so big it has other galaxies in orbit around her. Here's a very open, irregular, very thin galaxy, almost like just a star cluster, but much further out. I don't think it's this one, but there's one similar to this in which the dark matter content was 1,000 times more than the visible matter content of that galaxy. So we can get galaxies that are almost entirely dark matter. It would look like that, or less. Regular galaxies, as best as we can tell, these are the result of recent mergers of galaxies. You get erratic star formation regions, tidal interactions, and like that going on. It takes quite a while for things to settle down. There are galaxy simulators that you can download for your home computer and apps and iPads and like that. You can play with those. I had another thought there, but the thought has escaped me. What was the other thought? Oh, when galaxies collide, the chance of any two stars actually impacting each other is still virtually zero. I mean, they are so empty. When you have something the size of our star and the next nearest stars, and you have 4, 8, 10 light years of empty space in between, you might get some stars start orbiting each other. If they don't have too great of a relative velocity, they just pass and get flung about. But that's much more likely the interaction that occurs. The two stars get close enough that they kind of send each other off in a different direction. But direct impacts are almost unheard of.
In the upper left corner is a weird feature.
Oh, right there, yeah. Could be a supernova shell. It's possible. I don't know. Another irregular galaxy, a globular cluster here. That looks like it's more associated with our galaxy. It's in the foreground. Another irregular one. So these could be all galactic car accidents, so that we're seeing the pieces scattered all over the highway here. Hubble had an idea of galactic evolution, where he thought you had different branches of galaxies that eventually evolved into a more round appearance over time. We have not found that to be true in numerical simulations of galaxies or other features of the galaxy. So that's an old idea. So if you do see older charts that have that, then probably more likely you get just some evolution of formation as time goes by, from young galaxies, elliptical spirals and regulars, from 0 up to 12 billion years. There's some internal structural change. In the very long term, what gives these things existence to us is the light we see from them. And hydrogen, helium, and star formation will eventually peter out, but the universe is too young for that to have happened much. We'll talk probably next time about... Thank you. Well, just a little bit more. Let's keep watching your movie and we'll get going in just a few minutes. We're getting kind of there. But we have active galactic nuclei in which the black hole at the center is eating a lot. And it has a very, very active accretion disk. It's throwing out a lot of highly accelerated, highly heated material that can blast out a lot of the gas and dust from inside the galaxy and get large jets and features of material thrown out. And it's even possible, theoretically, that these things can sterilize all the life that might be in that galaxy. So if the black hole really gets crazy, things get disrupted, active galactic nuclei like this are very dangerous places to be near. So don't travel to one if you get the opportunity. So galaxies in general, how do we figure out how big these things are? We'll probably kind of work through this topic and we'll call it a week, a month. But light years are now getting pretty small, and parsecs are pretty small. Having to use hundreds of thousands and millions and billions gets sloppy. So we switched to megaparsecs. 1 megaparsec is 3.26 million light years, 2 times 10 to the 19th miles. The Cepheid variables that we talked about earlier can be seen for about 200 megaparsecs. So that's a good chunk of the universe. That lets you directly measure the brightness of an individual star in another galaxy 200 megaparsecs away. So that's about 0.6 billion light years, with the universe being about 14 billion light years in radius. So that's a good distance out. And again, Henry Leavitt published figured these out in 1908 and published her results in 1912.
It's quite a resolution if you can see an individual star.
I know.
I mean, that's,
It really is.
yes.
So again, we got luminosity related to the period, and they're really regular. As I think the type 1 Cepheid variables here. Now, to go further out, once you have all the nearby galaxies, you find the Cepheid variables, then you can look at the overall luminosity of the galaxy, the morphology of the galaxy, its shape, the relative size of the core to the disk, and other indirect things to start working out the luminosity of galaxies. And you can switch from stars, like Cepheid variables, to the luminosity of galaxies as one way to measure distances further out. We'll talk about redshift in just a moment, but as we're looking out, like we said earlier, the speed of light is really slow. The moon is 1 1/3 seconds away. The sun is about 8.5 minutes away. Alpha Centauri, 4 1/4 light years away. Andromeda Galaxy, 2.5 million light years away. In the edge of the universe, 13.772 billion light years away. So you're looking back in time as you go further out. So here's a location of our Milky Way galaxy 400 million years ago. Here's another galaxy some distance away. Say a supernova goes off. Now supernovas are another nice standard candle. When a supernova goes off with a certain decay, post-explosion, as the light goes down and vanishes from our point of view, you can figure out how bright the supernova itself was. If you get a Cepheid variable in there too, and you look at the size of the galaxy, now you have 3 ways to measure its distance. But the photon travels towards us, and as that happens, the universe is expanding. So now the galaxy's over here, further away. The light took this distance and time to get to us today, and we can see how it redshifted. So now we have a 4th way to measure galaxy distances. So we're building up our toolbox to anchor down our understanding of how big things are. Most distant galaxies visible, about 300 megaparsecs away, 10 billion light years. The record distant individual star that we've seen is a star we called Icarus. Gravitational lensing allowed us to see it very briefly as a very bright giant star. We saw it at 9 billion light years distant. Record galaxy right now we've seen is called GNZ11 13.39. Sorry, GNZ11. It's 13.39 billion light years away. Once the James Webb gets up, we hope to see a lot more of these. But what we get to now put together is the Hubble law, assuming that they. Okay, we'll take care of that in just a little bit. We're almost done. We look at the expansion of the universe and we assume it's a constant. A Hubble constant is the expansion rate, so how fast these things seem to be going away from us in kilometers per second, more so every megaparsec that we look out into the universe. And we're going to look at the details of this in just a little bit. Early estimates that were kind of favor around 70 to 80, but we've refined this further. So once you get that, then you can plot galaxies out there and look at start figuring out their distances and their speeds. So putting the whole thing together, we start with the Earth. We use radar to measure the distance to the planets. We time the rotation around the sun and different bodies in the solar system. And we can start to piece together exactly how heavy everything is and how far apart everything is, and nail down the speed of light from errors in the position of Jupiter's moons as Jupiter goes at different distances from us. Once we get the solar system really figured out, we use parallax and the motion of the Earth around the sun throughout the year, have nearby stars moving back and forth against much more distant objects. As we piece that together, we start to piece together the main sequence of stars. We know their brightness based on their spectrum, and that can allow us to get up to the Milky Way in size. We have overlap with Cepheid variables that take us out into the galaxies, and nearby galaxies. Brandon, sit down, please. And from the nearby galaxies, we can start looking at supernovae that occur, white dwarf nova, and galaxy size and morphology, and the expansion of the rate of the universe to go even higher up. Okay, Brandon, shh, we're finishing in just a minute. So with all this overlap, if you went out and figured out how parallax has always been wrong by 0.5%, then the universe changes in size. Because instantly everything that built up upon that changes as well. All right, look at the time. I think we may have pushed this. Yeah, we're 10 minutes till. Let's get to active galactic nuclei and other phenomena and the bigger universe next time. So, thank you all very much.